Thank you.
Thank you very much. I'm really looking forward to giving a Blackboard talk after 2 years of working in Zoom. And as Chen Cheng just said, that's really our sport. Our daily sport in math is writing on the Blackboard and wiping it. So I even enjoy getting my own water now. And ESI is probably one of the leading institutes when it comes to Blackboard real estate. At least I don't know any other with blackboards in the toilet. Okay, also I'm going to honor, so thank you so much for the invitation. I'm going to honor the topic of this workshop by actually talking about both parts of the title, about higher structures and field theory. So this is going to be about, when you work in higher structures, you often develop formalism, and then you have a formalism in search of a problem. So here it's completely the other way around. So the problem is motivated by this is a very old and fundamental problem in general relativity. So in GR, we have a diffeomorphism symmetry, but Noether's theorem does not give rise to a Hamiltonian momentum map. This problem has been around since at least 1962 and has motivated hundreds of papers and still no solution, at least not in this direct way. And of course, it's fundamental and I would also say highly annoying that we haven't fixed this. This is a project with a student of mine, Janina Bernardy, and also it's a spin-off of a long-time project with Alan Weinstein and Michele Schiavina and also Marco Fernandez. Okay, so so the first part of the talk, I will explain the problem. And I will explain a way from the viewpoint of a higher structures person that also already suggests the solution. And in fact, which has been lost to some people, multisymplectic geometry as a field was motivated by this very problem, and actually created by this problem. Okay? Even though now it has taken on a life on its own in differential geometry. So what's the setup? So I have a space-time manifold. So my setup, minimal setup for classical field theory, Lagrangian field theory, that is enough to formulate this. That's the right setup here. So I have a space-time manifold, I have a configuration bundle. So curly F, that's the sections. It's my space of fields, and space here will mean diffeological space, but that's not important for this. I have a Lagrangian, so that map takes a field and maps it to top degree form. Not orientability in these kind of questions are not important for this talk. So where n is the dimension of M. So something you can, well, if this exists, can integrate over, so you take L, evaluate a field, you get a top form, you integrate this, and this gives you the action. And here the first problem for me as a mathematician arises. This is generally not defined, but I'm going to add this as an assumption. Yes, it will be local. Here, I don't need it yet, and local or not, this thing generally doesn't define. It doesn't exist unless you make strong assumptions and also unphysical assumptions on M. So if you have boundaries, you have to work out new boundary theories like Michele Schiavina and like BFV and Cattaneo and Neff, Reshetikin. You have to deal with this, or you're claiming you have something that you don't have. That's often what happened in physics. And in a talk in this, together with the action principle, Graham Siegel once called in a talk in Bonn the mythological picture of classical field theory. That's supposed to be somehow true, but isn't, but generates the right idea. So now I add locality, as Alexei said. So now I view my L, and view it as a 0 n form in, if you accept this to be to work like a manifold in this product, Here, it's a bicomplex. And now I'm going to add loc. And by definition, setting aside a few technicalities, that's just the variation bicomplex. So that's the forms, so with also PQ here, of the infinite jet bundle of this. Okay. What? So this is 0n. No? Local. That's by definition. That's nothing horizontal yet. Well, that's 0 degree in vertical and n degree in horizontal degree. Yeah, horizontal, that's if you want to. That's just a special case. So here on this omega PQ, that's the stage of Lagrangian field theory. I have two differentials. I have the variation in p direction, that's the field, that's the dram, if you will, dram differential in the direction of the first vector f. And you have the, which I call d, the dram, the spacetime differential. This can be made rigorously sense of. That's another talk. So if you just believe me, as if you read the notes in the linear free string theory for mathematicians, they, just suggest that this should magically be all right. Okay, but you can make sense of this. Okay, that's a complex, bicomplex, sort of subcomplex of this somehow. So you can make sense of this, and that's now rigorously defined. Anyway, so now in the first, so to get you a bit into the spirit of this. So now I'm claiming, again, general relativity, when this is, for example, not closed or not compact, these integrals don't exist in all of the space of fields. So this, as a mathematician, I'm not very happy, but we can reformulate all we do, including the action principle derivation of the Euler-Lagrange equation in cohomological terms in the sky. I just have to state it properly, and what we avoid. So if you think about derivation of the Euler-Lagrange equation, it's all about discarding exact terms, the exact terms, so space-time exact terms under the integral. You never need to integrate for this process. So let's do this in cohomology and not pair with the fundamental form of M. That's what creates the problem here. And later, this is a relatively mild issue, but I'm just trying to motivate. The next step is that you make an unnatural choice of submanifolds. That creates the real problem for which we need higher structures. Okay, but let me formulate the cohomological action principle, or the action principle in cohomological form. So first I say form, it's a pretty obvious definition, okay, form in this bicomplex so you can insert again infinite jet bundle, but this is kind of more suggestive of the gradings and the bigradings. Okay. So this the form in here is the exact space-time differential exact at a field. Well, if there's another form such that alpha minus d beta, another form beta, let's write like this. If alpha evaluated phi, you have to make sense of this. Hard. This the d of beta, but just when evaluated at phi. Okay? And if you do this, then here's a little proposition. Phi is a solution of the Euler-Lagrange equations if and only if dl, I'm making all this to avoid integrals, okay? If dl is exact at phi. Okay, so that's relatively straightforward. It's just a conceptual thing. No, also for p equals 0, it's very easy. It's the pullback along the infinite jet prolongation of the field phi. If it's not, you have to work a bit more, but this can be done. Okay, we're gonna use it for that case, and that's why I'm not going into detail here. I can explain to you in the break. but it's also possible. Okay, so now Noether's theorem. Noether 1, so now we have the variation of our Lagrangian, and we can split it into the form that contains the Noether-Lagrange equation minus the boundary form. That's what we discard under the integral. So we're now EL is a 1 n form and a Lagrange form. This is a 1 n minus 1 form. That's the boundary form. And in order to formulate Noether's theorem, I need another notion. There's a slight thing I have to observe. I'm talking about symmetries. Now you can immediately guess what the symmetry of in the cohomologic sense of the action is. You take a vector field on your space, so let's say J infinity of F. You apply the Lie derivative to L, and that should be d-exact, which would mean if the action exists and you can integrate, it's going to be a critical point of the action. So, little definition, a vector field X. This is called strictly vertical or horizontal if, so now I'm saying this, this goes by different names, equivalent to more familiar in variational theory, to more familiar constructions. But I just need this algebraic relation. In the Cartan calculus, if the vector field commutes with the horizontal differential, the inner derivative, or the vertical differential, and it's called strictly horizontal and vertical. This, if you figure this out at least in J infinity of F, well, first, here's an exercise. If you have a product manifold X cross Y, you will see that this exactly characterizes the vector fields just on X or just on Y, lifted with the trivial connections. So that's the idea. And if you figure this out, these are, this is evolutionary. Well, the prolongation of an evolutionary vector field, it's the same as a local vector field just on F. Also the same as saying evolutionary. And this is the lift by the Cartan connection of vector field on M. Okay, so that's what you, pardon me? Exactly in this language. Okay, so now Noether's theorem. So for which you need this boundary form gamma and your notion of strictly vertical vector fields. So if this is a symmetry, i.e., what does this mean? Well, the Lie derivative on L is the d of something, so it would vanish under the integral, and Noether, I have to add that this is strictly vertical. Strictly vertical, then following thing. This guy, so where does it live? In 0 n minus 1 degree on J infinity of F. So you can view it as eating a field, 0 here, producing something in degree n minus 1, so a current, something you can integrate over time slice. This is a 0. Yes. But there's a whole complex, and this specific guy is in 0. Oh, wait, sorry. Yeah, here it's 0. Right. Handwriting, perhaps, so that's the Noether current. Then this is E-closed on shell. So in other words, that's your space-time, and you have a surface, and you have a time slicing, so that's like the surface at 0 and at t. So being on shell means you plug, being declosed means you plug in phi, and the resulting form, the integral of the resulting form only depends on the homology class. So it's the same whether you integrate here or there. So if you define the charge, depending on time, as the integral, so the charge at phi is the integral over sigma t of j phi, then this, that's the Noether charge or momentum perhaps. Then j conserved means that q of t is constant, doesn't depend on time if phi is in shell. Okay, so it's really conserved in the true sense. Okay, so here's to talk about Hamiltonian momentum maps. So this is your momentum map, right? Natural candidate for momentum map. And by definition, that's, I haven't checked, but you can check, but, oh well, okay, before I say this, right, before I talk about Hamiltonian momentum sections, momentum maps, I need to introduce the symplectic or presymplectic form. Perhaps Poisson form here, the natural one is presymplectic. So here's an observation. That's what most people use, and we will not later because you'll see it's not the good one. If you think you know where this is headed. So this variation of this boundary form gamma is now that as a 2, n-1 form. You can view it as a current with values in 2 forms on the space of fields. Is conserved in the same way. So this means if you integrate this over sigma, this is pretty independent of the choice of sigma. It depends only on the homology class. So mildly, it depends mildly on sigma, okay? So this is now true from its close. It's even exact. These operations commute 2 form on F. Okay. Now we can talk about, now we can ask the question, is Q, the charge, the Noether momentum map, is this the momentum map actually? So the first one, does it generate the symmetries as Hamiltonian vector fields? Yes, but unfortunately, this is not does not preserve the bracket. Q is not variant, so not compatible with bracket, which you get from the presymplectic form. So of course you have no Poisson structure, but even for a presymplectic form, you get bracket, well-defined bracket on the Hamiltonian functions. And this is the problem, and this is seriously bad, right? That's the structure we want to quantize. That's the structure somehow. I mean, if this is not compatible with the symmetry, this leads to lots of problems down the road. For example, identification of the physical degrees of freedom in any quantum gravity theory. Anyway, so this is just a math problem here. I'm posing to myself. So the way I've written this, it's clear if you're a higher structures person, choosing the sigma, no matter that the omega doesn't depend a lot on this, obviously breaks the diffeomorphism symmetry of your theory. Clearly, the diffeomorphisms don't leave any of the sigmas, not all of them, any of the sigmas invariant. So, well, you're making an unnatural choice, and that's one of the effects of this, that the bracket is not preserved. And as I said, there are lots of papers of this. They all come down to the same problem. So this is why in the 60s, people started to think, okay, before we really properly had high structures, let's not make the choice. Right? So let's, instead of work with this omega, this 2 form, in the presymplectic world, let's work directly with this del gamma, this higher form, and pretend it functions like a like a symplectic or presymplectic form. So this was the advent of multisymplectic geometry, a multisymplectic approach, let's call it this, okay, to this problem. Most famously, the Jimsy projects, Gotay, Maaßen, others, Netitsky, and so on. It was an internal, never finished project that was influential, but tried to attack this problem. So now, so what's the situation? I'm now going away from the field theory and just remind you what multisymplectic geometry is, just on a manifold, right, to not obscure the easy geometric things we're doing by this additional structure of the field theory. So let's say we have an n+1 form on some manifold. So we call this then like pre or multisymplectic form. The difference between pre and like not pre is not so big in this word, so I won't make a fuss of it. So here's the obvious definition. So a vector field on X in the form are called Hamiltonian if, well, nothing changes in our definition. If the usual relation holds, and you see this implies that the degree of alpha is n-1. It's not a Hamiltonian function, but a Hamiltonian form. Then we can try to define the brackets. So we say, okay, the two bracket of two such forms, alpha and alpha 2, is, as we do it in the presymplectic or symplectic case, is omega. That's the corresponding Hamiltonian vector fields. But this does not satisfy Jacobian, even though it's fairly easy to fix, as I explained a second, by an L-infinity structure. Well, I mean, the guys who started this we were in the 60s and 70s. You shouldn't expect them, to come up with this before L-infinity structures were properly invented and understood. So this was what was lacking in the early approaches to multisymplectic approaches to field theory. So they did everything with this, let's say, like this somewhat weak notion of homotopy, using homotopy in the sense of up to some exact terms. And we know this is not good enough. We need to control the failure, okay, for these structures to survive, to form model category structures, survive quasi-isomorphisms and so on. So here's the fix. First in the thesis of Chris Rogers. So we define the following, given the structure here, the following graded vector space. So we start with these Hamiltonian guys. Top degree, then it's difficult to say what Hamiltonian means in lower degree, so we just fill them up with ordinary forms. This will do. So no Hamiltonianist condition here, all forms, all the way down to functions. And we have as brackets with L1 of alpha being d of alpha. Well, that should be the differential in our homotopy setup. And the Lk, alpha 1 alpha k, only defined for Hamiltonian forms and in the way you expect. Just plugging them in. So that's a bracket, and 0 otherwise. It's a very sparsely defined L-infinity structure, but it's good enough. And the statement is this, blah, 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 that great vector space with these brackets is an L-infinity algebra. Okay, very good. So now we have I can leave this here. You have the structure we need to talk about, I could say, algebraic compatibility of a momentum map in a nice homotopy algebraic way. So here's the definition. That rho. So in all this game, we don't define. This is only defined for Hamiltonian forms, and these are the corresponding Hamiltonian vector fields. And these, yes, and if you have only one of them not Hamiltonian, this is zero. That's what I mean by zero. Otherwise, it's really these brackets and a bit of fluff to accommodate for the exactness in the lower terms. Okay, so of course we have to convince you at some point that this is actually useful for in field theory. That's my promise. Let's define homotopy momentum map for an actual action, and I'm not going to higher actions of higher L infinity algebras. So the thing acting is always an ordinary Lie algebra. Okay? So here's just an action, an x with this omega. So a homotopy momentum map is morphism of L infinity algebras. So this, let me spell out, this is just a family of morphisms. So let me perhaps write it. I'm going to write like this. It's the same as this L infinity division. I think the grading somehow is, can be redefined at this degree 0 for convenience. I write the natural degrees so that you see what the objects really are. So this goes to n minus k such that, well, it should, of course, the mu1 should really generate the vector field. So with d of mu1 of a is, that's a convention here in the business, should be the Hamiltonian vector field. Okay? For all A. So this, just the mu1 was what was called for 40 years or so in the business, was called the multi-momentum map, where then people said, well, this is preserves the bracket up to some exact terms, but it wasn't even clear what the right structure in the target should have been. Okay, this was missing if you look at the older literature. Okay, so now here, one thing that well, that's a lot of structure if you now want to find a momentum map, right? It's just not a mu1. And if you think you have, okay, these act by Hamiltonian vector fields, in the sense just described, you say, for usual momentum map, it becomes a yes-no question whether this preserves the brackets or not. Not so here. It's all the other guys you have to find and construct. So this is certainly much more structure you have here. Okay, so a special case, which will turn out to be relevant, is that omega is exact, and rho, fundamental vector fields of the action, leave already the primitive of the multisymplectic form invariant. Then mu k mu1 ak defined as, well, then the lambda itself is the homotopy momentum map. It works in the same way as in the symplectic case. So plugging in the vector fields into this primitive lambda is, well, it's an L infinity morphism. It's quite a few things to check, but this works out. Is a homotopy momentum map. Why is this interesting? Because we'll see later that the symmetries for symmetry R have this property. Okay, that's what I'm going to use to construct the homotopy momentum map. Okay, so back to Lagrangian field theory. So, if you want to apply this to field theory, there are two immediate questions we have to figure out. So, question one: what is the right multisymplectic structure? And right, of course, means different things for different people, and right for what we want to do. What's the right omega? What do we have? We have lots of forms hanging around. We have the Lagrangian, we have the relation of the Lagrangian, we have the Euler-Lagrange equation, we have the boundary form, we have the gamma. I think this is the popular choice, the gamma. This would be the choice in factorization homology. It's also not out of the question to take L itself. So which one to take? And also, what differential, just the horizontal or the vertical, or let's call it like this, the total. I think with this choice, you would typically take the horizontal only. And question two, what action to take? So there also we have, so as I said, this whole thing was developed for theories with diffeomorphism symmetries where the choice of a Cauchy surface manifestly breaks the symmetry. So when you have a diffeomorphism symmetry, and typically then your bundle will be natural, so your diffeomorphism lift to your fiber bundle, you have an action F, you have an action M. You have a diagonal action on both of them. Noether's choice would be just the action of F. That's why I'm insisting on this point of view. So for Noether's theorem, the choice is you just take the action of F, you take dl, you take only d. So how do we figure this out? So here's the proposition. Well, now we throw this multisymplectic definition at it and see. So here, after trying this bit out, I think the right choice is the following. So this is my omega I'm going to take, del plus L gamma. So I have an Aufscher term and the usual boundary term. I take the differential to be the total differential, which is truly the Dram differential on the infinite jet bundle. And then a vector field is Hamiltonian if and only if two things are true. One, it leaves omega invariant. That should be the case. This is 0. And two, that if I plug in the vertical component of X, right? So it's a bicomplex. Works like a split manifold vertical component into EL. It's d of j, where j is the ordinary Noether current. So I would say this is the right choice because the homotopy momentum map because this is actually the relation you have for ordinary Noether currents. That's how you could even define them. Noether current is a vector field, vertical vector field such that this holds. And then you can work backwards and see that comes from Noether's theorem. So this means with this choice of multisymplectic form and differential, your Hamiltonian condition in the multisymplectic sense gives you what you want. It's in first degree. It's this. Now you wonder, okay, so what happens? So is this all of this? Is this the generating function alpha? No. So let me write this in perhaps a color. So note the alpha this is just a conventional sign. And then there are alphas in other degrees. So this is a degree as we see, in n minus 0, n minus 1. This is in 1, n minus 2, blah, blah. And this is in n minus 1, 0. You need all these, and you get them by the acyclicity theorem of the ratio bicomplex, and it's choices you have to make. Okay, so another observation is, I'm getting close to wiping time. So observe that this omega, which is the EL plus del gamma, there is exact. It's a differential of lambda, where lambda is the so-called, some people at least call it the Lepage form. Funny? It is totally degenerate. There's nothing non-degenerate. In multisymplectic geometry, what does non-degenerate even mean? Like for dimension reasons, there can nothing be truly non-degenerate. And you could say that the map where you insert a vector field into the form is at least injective. That's the definition of multisymplectic. And it's, it's a reasonable condition, but it doesn't make you as happy. It doesn't make such a big difference as in symplectic, where you could have an inverse. What is non-unique? Sorry. The J only depends on the choice of gamma, which is a my choice, and then it's unique. The alphas are really choices that come from a lot of cohomology, decohomology vanishing. Only at the boundaries it doesn't vanish. That's this acyclicity. And the question would be, and that's an obvious project, and Alberto keeps bugging me about this, what does it mean, right? It should be the things that now give you something on the boundary theories, or if you go full cobordisms, like in the TQFT, on the boundaries of the boundaries and so on. So what do these alphas mean? But this is not a question I'm going to address today, okay? But that's an obvious one. Yeah, right. I agree. So, so here's the theorem that makes at least me a bit happy. So let now. So now, people keep asking me about gauge theory. From this point of view, gauge theory doesn't even have this kind of problem, right? You can find an honest momentum map in gauge theory, so you can go to higher structures. Why would you? In general relativity, there's no other way. So, or in theories with diffeomorphism symmetries. Yeah, that was the main reason to do it. So let's look at one. I don't know. I don't think so. I don't think so, honestly. Yeah, it's additional structure that could have relevant if you go back to boundary. The only thing I was claiming here was that for the original question of, going to your Noether theorem, then choosing sigma, then integrating, that you get a momentum, like something compatible with the brackets. For this, you wouldn't need it. That's all I'm saying. Otherwise, this is still in gauge theory also an interesting structure. I agree. So let now this be the phi-wise Lorentz matrix or spacetime and L. Be the Hilbert-Einstein Lagrangian. So then the following action. Vector fields on this infinite jet bundle of this that sends vector field 2. So a strictly vertical plus a strictly horizontal part where to explain. So this is the thing you expect. So this vector field should be a map from matrix to tangent space of matrix, just giving you the value of in the fiber, which would be minus the Lie derivative of the vector field. This to be in homomorphism of G. So just the standard action of vector fields on matrix, and this V hat is the Cartan lift. the point just being here, you need the action of both of space at the same time, and space-time and the field direction for this business to work off shell, right? So, wait, where am I? I have to use this to stay on message, to not tell you too much. Is so this say this is manifest symmetry. So this is a word coined by, I think, Janina Bernardy, and this means it leaves not just omega, this omega here invariant up to the exact terms, but it leaves actually the primitive invariant period, truly invariant. So Lie of rho some vector field V acting on, it's really two equations because they live, this is degree 0, this lives in 2 pi degrees. This is actually 0 with the proper choice of gamma. So this is a manifest symmetry, and as I've said before, this works since omega itself is exact. Now, where is it? A special case here, I can apply. So then, this is the hard part. Okay? The corollary is the GR. Let's write like this. I write as a sort of take-home message. Let's just write, we get, in this way, a homotopy momentum map of GR. And so I'm happy about this. Well, perhaps you can if you like relativity structures and don't think that is a mistake to go into this higher word. So, okay. Now that we have that, of course, not all is good. Now I need to wipe. When did it start? 10 past, or when did I start? At what? Ah, I see. Okay. So what do we now with this? What good is it doing for us? So perhaps a reminder is in order, which things you all know, is why. Why do we like Hamiltonian actions? Well, there are a lot of good things we can do with them. So in physics, they play a role if you want to talk about integrable systems. Or you have the correspondence between the Delsan polytopes and toric manifolds, or you have the Heckman theorem of integrating the symplectic volume, which is difficult in general, but can be easy with the momentum map. Or if you have Hamiltonian actions, you may have they enter the Tier-Bott characterization in equivariant cohomology, models of equivariant cohomology, for example. So what all of these things have in common is that they involve in one way or another symplectic reduction, and that's of course the first thing that comes to mind. And so now that I'm making a mess, I'm sorry. Maybe that was a bad idea. So the question is, what is this here in this higher world? That's now really the topic of the talk, right? So now what we have, So we have a homotopy version of this. Let me use a different color. Next step, so here we have it. So check here, but if you want to do reduction, there are more things involved. So we would need, first thing, zero locus. Right? So what is a homotopy zero locus? And perhaps we would want this to be isotropic. So what would it even mean to be homotopy co-isotropic? And then once you have the zero locus, we would perhaps also show that it's invariant. And then we want to take the quotient, so invariant under the action. And here, as I said, I have an ordinary Lie algebra action. This won't change much, okay? So they don't need homotopy versions. That's just ordinary Lie algebra, ordinary invariance, ordinary quotient of perhaps a group if it's in some sense the compatibility of the homotopy momentum map with omega raises to the group level, which, okay, of course has to be defined. So let's start with the zero locus, which is a bit puzzling at first. So let's do this here. So if you think about momentum maps in ordinary symplectic geometry, there are various ways of encoding them mathematically, have advantages and disadvantages. The most popular choice is map from the manifold to G dual. The one we have somehow used here in the generalized version is the one from G to the infinity of X. So this, I write very sloppily. So what is this? The hom to X, G to R. We have from G, homs from X to R. And you're just using the exponential property of the homs to move this back and forth between. And so in the middle, you have the guy where you move this hom and convert this hom into a product of X cross G, or G cross X to R. So that's the third option. And really, this is just a piece of, we call this sloppily, I'll explain in a second, to the cohomology theory in which obstruction theory for momentum maps lie. So here, this is obviously the best, the left-hand side, to define the zero locus. So the zero locus is simply the inverse, literally, of zero. So here it's much more complicated already. C would be, so all points, such that if I take mu, apply to A, evaluate at X, is zero, but now for all, it's the common zero locus for all A and G. And okay, so this is like the two obvious things I can do. So what is now with the homotopy zero locus? So what about this formulation? Well, unfortunately, this is really and unretrievably gone in the homotopy setting. This picture of the momentum map simply doesn't exist. And this is the one we've obviously used by replacing this, which with the Poisson brackets is a Lie algebra, by an L-infinity algebra of Hamiltonian forms and this graded vector space. So this exists, and you might be tempted, to define it like this. X of X, and now you have mu. And you have all sorts of mu's with k's, and if you think a bit for a while, it's probably requiring this for all k's is much too strong. So you might require this for G, so it wouldn't be homotopy at all. It's just you say I take the first component, so the multi-momentum map, and I set this to 0. And this is what, that's a choice by AC Blacker, Nitti, Sambon, maybe Rifkin, that you can do, and perhaps in differential geometry. And this might be an interesting structure to do reduction this way. Well, we have a goal in mind. We want to do, want to understand the momenta in field theory, for example, the constraints, theory of constraints. So this should be the right thing for that. And there, of course, this is not the right thing. What would it be in the field theoretic case? You would require the currents to vanish, whereas clearly you should require the charges to vanish, right? Your zero locus shouldn't change if you add to the Noether current some exact thing, which would change the locus drastically. So that would be like the first condition. This should more or less have some part of the zero locus, or no, this should be the zeros of the charges. And so this is not what it does. So we need a homotopy version. So this is actually where this comes in useful. And this was worked out by Legier and Camille Laurent-Jangou and Marcus Zambon. They have realized that this we still have, and it's a good framework for the abstraction theory of momentum maps. And as I will now argue in my last 10 minutes, this is also a good framework to define the homotopy zero locus that does the right thing. So let me explain what this cohomological framework is. So now we have consider the following bicomplex. This was a sloppy notation. It means the RAM here, surely Eilenberg there. Okay, so let me perhaps state this properly. So this is this bicomplex with E is the surely Eilenberg Lie algebra cohomology plus the RAM. That takes into account at the same time the algebraic properties and the geometric properties of the target manifold. And in this, we can view mu. We can take the sum of all the components of the sorry, that was this really poorly written X. I don't want to call it M because M is my spacetime, and later you should think of X as F cross M, fields and or the infinite jet band. That's why I'm using the somewhat confusing Hamiltonian vector. Funny? Well, it's just yeah, but it's not two copies of this. Okay, it's just the usual. You could view it as it's what I've just written. Exactly, yeah. Okay. Well, the veil if you've divided out sort of one of the invariants on one of the factors. Okay. Yeah, if that's, I think that's what you mean. So now you can, so very naturally, this, all the components of a homotopy momentum map can be lumped together into one big thing. That looks like it could be convenient. So this is now just in total degree n, and now you have to see how this is, how this is connected to the presymplectic form. There you can define this guy, which is in 1 degree higher, of course, and it's defined as, so let's see how my low-tech way of defining it. Omega k is just inserting the action into the first k arguments of the omega. Okay? So let me write it as this, perhaps suggestively, rho. So this is k factors, and then the rest is you can plug in ordinary vector fields. and that's n plus 1 minus k factors. And that's these omega k's, and you need some signs. Not so important. Yes, the composition is really, this is 1, n minus 1, 2, n minus 2, and so on. Okay? And here, the same as you can read off here. And so the statement, the theorem by Piaget, Laurent-Jean-Goux, Zambon is, that's obviously very nice. So mu is a homotopy momentum map of omega if and only if E, should I use a fancy letter perhaps? Let's call this D bar. So D bar of mu bar, is omega bar in this complex. So very nice. Works as you would hope. So now, okay, maybe so this looks like it could be a better way of with the homotopy momentum locus, homotopy zero locus. So let me first for the ordinary so let me say for ordinary the G, yes, yeah. So in field theory, the Lie algebroids appear since like gauge groups and vector fields are sections by section algebras. Section algebras or bisection groups of Lie algebras or bisection groups. Yeah. Yes. Yes. Yeah. 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 Oh, sorry. This is what. Yeah. You could. Yeah. It suggests a lot of generalizations already when you write it down sort of in a nice framework, and then you see this, how you could generalize. Here I'm doing absolutely grunt base work, right, to show still my job is still to show that is what? What do you mean by naturally algebraic? Actually algebroid. Yeah, I'm not sure. Let me defer this, okay? But that's I think at this point the differential is okay. For this we don't need it. Okay? For notions of invariance we might. For say it again. It's a perturbation of. Well, not quite. So well, not really. So you would start with your Weyl algebra. Which you can view as T of G star tensor omega of X. Then by imposing the forms to be horizontal, first step, you get rid of this. That's why you have then really S. And then you take G. This would be the Cartan model. You have versions of this. But now you see it's different. This is really, you should view this. Yeah, I know this model, yeah. No, it's not. No, it's not. We can talk about, I will tell you what for me BST model is: functions on T bracket 1a bracket 1 with the differential that is the Ram differential plus the prolonged Lie algebraic differential. That's the BST model. And now in this, you have to look for the basic subcomplex. That's not that. Sorry, but this, I mean, maybe in specific cases. Okay, but we can talk about this, okay? I have another student who works on exactly that, okay? So, let me maybe give you the upshot. Okay, I give you already the definition of the homotopy locus. So homotopy locus on all of X doesn't make sense because up to the X, I mean, the cohomology is inherently non-local. This wouldn't make sense here. If you compare this to field theory, we want this to be exact in space, in the space-time direction. We want a field to have this property with respect to the space-time direction. So you need a splitting of sorts. So now you can define this. If your manifold is split, then you have a relative homotopy zero locus. Let me define this, and then I'm going to give you the theorem that tells me that this might be useful. Okay, so let this. I'm taking this L infinity. Let's write it as the natural target. Okay, and minus k, and now it's a product manifold. Okay. Like a homomorphism of infinity algebras. Doesn't need to be a momentum map to define this. And let I at a little point x, let for x in x. Later you think of this as a field. Okay. Let this consider the following map. You just map G cross X cross Y into the thing on which this cohomology lives. And now you have the pullback on forms, which would be somehow restricting this form to X in this direction. So point is in the, let's say, Y homotopy zero locus. If that pullback is dy exact. So if of this mu, I already have the if, so this thing pullback applied to mu is dy exact, period. Well, that's the definition. It's specifically designed to work A, to give the right thing for field theory, and B, only operate with natural constructions in cohomology. Right, so I have a pullback. That's all cochain maps. This is why I'm doing it like this. Could have easier definitions that wouldn't make it as transparent. So okay, so let's check GR, for example, works for, let's make a more general statement terms. Let A be Lie algebroid. So F, some configuration bundle Lagrangian and LFT, local Lagrangian field theory, and row from the sections of A, so the Lie algebra of sections of A, two vector fields of J infinity of F, be a hamiltonian local symmetry, which means that, well, on the target's loco, I plug this into the domain explicitly, but also that map row is loco. That's a space of fields, and I require this to be locally differential operator, as is true for diffeomorphism, symmetries, gauge symmetries, and so on, or most symmetries, many symmetries we care about. Then the field is in the M homotopy locus of the momentum map. I haven't named it. Of the momentum map if and only if Noether charges, like if all Noether charges of I vanish. This looks reasonable, and it uses the vanishing theorem for the charges of this. I don't know what it's called, Noether 1.5 or something. So this, is a hint that this might be the right thing. In field theory, the next step is to show that, well, to equip this with some kind of smooth structure and show that the fundamental vector fields are tangent to the zero locus. And the way you can do it, you can use the definition of homotopy zero locus, which suggests a very natural diffeology. It's not the subspace diffeology. It's a diffeology that uses sort of families of the exact terms on the right-hand side of things being exact. And then you can actually show that this is invariant under G, which is not obvious at all. And so you can at least take the quotient, and that's where we are. And then you can continue with your program. At the end, if you understand this properly, what you want is some kind of universal ADM structure that is in sort of a well-defined, not symmetry-breaking algebra geometric higher structure that has the function that if you plug in a choice of a Cauchy surface, it gives you the ADM Hamiltonian formulation for every sigma. So this is what you would hope to get at the fantasy end of this project.